Kia ora all. This video is going to take you through the thermochemistry derived grade exam for the year. Starting with question 1, write electron configuration for atoms and ions. So, in year 13 we learnt that electrons, the shells that the electrons go in are no longer as simple as 2, 8, 8, 18. Those shells are actually broken into slightly smaller subshells, which we call S, P, D and F. And those subshells can hold different amounts of electrons. S can always hold 2, P can hold up to 6, D can hold up to 10, and F, which we don't get in year 13, can hold up to 14. So this is how I always do electron configurations. You can do it your own way, they're all correct, but I lay out the different S, P, D subshells. So bromine, if you look it up on the periodic table, has 35 electrons, and when we're doing configurations we go through and fill up the lower energy first. So fill up the 1s first, then the 2s, 2p, 3s, 3p, 4s, 3d. Now the interesting thing about electron orbitals, while we're at this point, is even though 4s is an extra energy shell, it's further away from the nucleus, it actually has a lower energy than the 3d one. So that's why we put electrons in the 4s before we do the 3d. At this point I'm just going to tally up how many electrons I've used. I've got 2, 4, 10, 12, 18, 20, 30. I've used 30 electrons. I have 35, which means I have 5 electrons left. So they're going to go in the P1, 1, 2, 3, 4, 5. Okay, so my electron configuration is a summary of how many electrons are in each subshell. So in the 1s there are 2, 2s, 2, and 2p there are 6, 2, 6, 2, 10, and then 5. Alright, on to iron 2+. So when I do ions, I always treat it just like an atom. I do the atom first, and then I either take away electrons or I add new electrons. So we've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Iron, sorry, I forgot to say, has 26. An iron atom has 26 electrons. So that would leave us with 3d6. Now, when you lose electrons, this is another anomaly. When you lose electrons, you always lose from the 4s electrons before the 3d6 one. So you lose the electrons which are furthest away from the nucleus. So what that means is these 4s2 electrons, these are the electrons that go first. So you're left with the configuration of, at the end, 3p6, 3d6. Scandium, 21 electrons. Just go through the same process. 1s2, 2s2, fill up the lower ones first. And when you get to this point, you've used 20 electrons, which means we've got 1 electron left in the 3d. Alright, part B. First ionization energy information is given below. You can see that bromine has a higher ionization energy than gallium. So the first thing you need to do is define the term first ionization energy. So what it is, it's the energy required to remove the outermost valence electron from 1 mole of atoms in a gaseous state. And you have to get across certain things in your answer. You have to get energy required to remove, you have to get valence electron, you have to specify 1 mole of atoms, and you have to specify gaseous state. And if you miss any of those, then chances are you're not going to get the mark for the definition. So in terms of the table that we're given, what it actually means, because the value for bromine is higher, that means it takes more energy to remove 1 electron from a bromine atom than a gallium atom. And the next question is asking us to try and justify why that is with reference to the configurations. So first thing you notice when you're comparing these is that both of them are in the 4th period. So what that means is they both have valence electrons in the 4th shell. And the implications of that are the electrons are a similar distance from the nucleus, and that they have similar shielding because they have the same number of shells. What's different between the two is that bromine has more protons than gallium. So bromine has 35 protons compared to gallium's 31. So what that means is it has a stronger nuclear charge. And nuclear charge, kind of think of it like a magnet. Because there's more protons in the bromine nucleus, there's a stronger positive charge, stronger magnet, it's going to have a stronger attraction. So because it's got a greater nuclear charge, it's got a greater attraction to the valence electrons, this is where I stuffed up. Because there's a greater attraction to the electrons, it's going to take more energy to remove an electron, and therefore it's going to have a higher ionization energy. Now this thing that I forgot is actually really important, and if you're after merit or higher, you need that. You need to link the attraction to the energy needed to remove it, because that's what ionization energy actually is. Now what's interesting about this answer is, get this right, the stuff that I've put in the box, that information there is the same for an atomic radius question, an electronegativity question, and an ionization question. Okay, it doesn't matter which of those three they ask, the information in the box is always going to be the same. The only thing that differs is that last little bit. So trying to link it to ionization energy or electronegativity or radius. Okay, the actual things that affect it are the same for all three. So jumping on to the next one, you're given the electronegativity and radii for chlorine and bromine, and you have to talk about the differences. So you can see from the numbers that chlorine has a smaller radius, it's a small number, but its electronegativity is higher. So first thing is talking about the differences between the atoms. So both are in group 17, which means they have the same number of valence electrons, but the difference is bromine is in group 4, period 4, sorry, so it's got 4 energy shells, whereas chlorine only has 3. What that means is for bromine, the valence electrons are further from the nucleus, and because there's an extra shell, they experience more shielding from the nucleus. And the effect that has is it means the attraction between the nucleus and the valence electrons is less for bromine, and that's despite it actually having more protons and a larger nuclear charge. Okay, so there's two kind of things up here that cause the attraction to be less. This thing here causes the attraction to be more, and when you add them all together, these things are the ones that have the bigger effect. If you're after merit or excellence, you have to state this point. So despite bromine having more protons or a stronger nuclear charge, the overall attraction is actually less. Now, in terms of relating this to the question, we're meant to talk about the radius and the electronegativity. So to talk about electronegativity, you need to define it first. You need to say what it is. So electronegativity is the attraction between nucleus and bonding electrons. And up the top, we've just discussed that the attraction for Br is less. So Br has less attraction to bonding electrons, or valence electrons, because the valence ones are the ones that bond. Therefore, it's a lower electronegativity. Right, in terms of the radius, I'm going to talk about why chlorine is a small atom. So chlorine, as we discussed above, is going to have a stronger attraction to the valence electrons. So because bromine has less attraction, chlorine is going to have stronger attraction. Because it's got a stronger attraction, it's going to pull the electrons in closer, and as it pulls them in closer, the radii decreases, or it becomes smaller. On to question 2. We're given 2 compounds and asked to draw Lewis diagrams for them. So Lewis diagrams very similar to what we did in year 12. 2 differences. Number 1, we can do Lewis diagrams for ions, so things with a positive and negative charge. And the second thing is, in year 12, you learn something called the octet rule, where basically all atoms are trying to get 8 electrons. There are actually some atoms that can hold more than 8 electrons. So anything bigger than silicon on the periodic table can actually expand its octet and hold, in our case, up to 12 electrons. Anywho, going through Lewis diagrams, first thing you need to do is work out how many electrons or valence electrons you have to play with. So sulfur, group 16, can give us 6. Fluorine is in group 17, so it can give us 7. There's 3 fluorines, which is 21. And because it's a positive ion, it means we have 1 less electron than you'd expect. So we take away 1. Gives you a total of 26 electrons. So put sulfur in the middle, surround it with the fluorines. First step is to put in your bonding pair of electrons, and you then fill up the outer atoms first. So you go around, make sure the fluorines all have 8 electrons. Once you've done that, you work out how many electrons you've used, and we have used 8, 16, 24. We started off with 26 electrons, so that means we've got 2 left, and they're going to sit around this sulfur. Okay, because it's a positive ion, we're going to stick the whole thing in brackets, and we're going to give it a plus charge. Next up, SF5 minus. So sulfur again gives us 6, each fluorine gives us 7, 5 of them, which is 35, and because it's a minus ion, it means we've got an extra electron, so we go plus 1, which gives us a total of 42 electrons. So, put sulfur in the middle, surround it with fluorines, same as before, put in your bonding pairs, and then make sure each fluorine has a full shell of 8 electrons. Once you've done that, you add up how many electrons you've used. We've used 40, 8 times 5. We started off with 42, which means we've got 2 electrons left, so we're going to place them on the central atom, which is the sulfur. So you'll see in this particular case that sulfur has 12 electrons around it rather than the normal 8. Your last step, because it's a negative ion, we're going to add a minus charge. Next part, you're given 2 Lewis diagrams, and you're asked to compare and contrast the shape and polarity of these 2 molecules, include a 3-dimensional diagram of each, of the shape of each molecule in your answer. So first things first, looking at the shape of the molecules. The thing that determines the shape is how many regions of charge are around the central atom. So if you start with SF4, it has 5 regions of negative charge. It's got 1, 2, 3, 4, and the lone pair is 5. So those 5 regions repel to try and get as far apart from each other as possible, and when they do that, they go into a trigonal bipyramid arrangement. And what that looks like is 1 up, 1 down, and then 3 kind of in the middle in the plane, in the triangle. Of those 5 regions, 4 of them are bonding, 1 of them is non-bonding, and that gives you a seesaw shape. Looking at SF6, it's got 6 regions, 1, 2, 3, 4, 5, 6. They repel into an octahedral arrangement. Octahedral, 1 up, 1 down, and then 4 in the middle, in a square. All 6 of those regions are bonding, so the final shape is octahedral. So we've talked about what causes the shape. The difference between the 2 shapes is SF4 has 5 regions, SF6 has 6. In terms of polarity, both of them have sulfur-fluorine bonds, and those bonds are all polar as fluorine is more electronegative than S. And because one's more electronegative than the other, it creates a bond dipole. So the sulfur is slightly positive, and the fluorine is slightly negative. So for a molecule to be polar, you need 2 things. You need these bond dipoles to exist, and it depends how those bond dipoles are arranged around the central atom. So they both contain bond dipoles, but because in SF6 they're arranged symmetrically around the sulfur, they cancel out and the molecule is non-polar. So if you look at SF6, each of these 6 regions is a bond dipole, but because they're all spread evenly around that sulfur, they actually cancel each other out and it becomes non-polar overall. Compared to SF4, if you look at SF4 shape, which is a seesaw, that is the bond dipoles are arranged asymmetrically around the sulfur. So they're not spread evenly around, they sit on a particular side of it. So because they don't cancel, that makes the molecule polar. In terms of the shape, let's go back up the top. SF4 looks like this. You don't have to include lone pairs of electrons for it, so it literally look like that. And SF6, just fill up every region with a fluorine. Alright, next question. Compare and contrast the bonding points for each of the following compounds. So there'll always be one of these types of questions, and you need to be able to look at a chemical and identify what type of intermolecular forces are there. There are 3 types you need to be aware of. Temporary dipoles, or instantaneous dipoles, permanent dipoles, and hydrogen bonding. Okay, so you need to be able to recognise which of those 3 are present. Basically, temp dipoles, they exist in any molecule. Every single molecule will have temporary dipoles. Permanent dipoles, they will exist when you have atoms bonded to more electronegative atoms. So if it's a polar molecule, it's going to have permanent dipoles. Hydrogen bonding occurs whenever you have a hydrogen which is attached to a fluorine, an oxygen, or a nitrogen. So in this particular case, we're given propane and nonane. You need to recognise that these are both alkanes, and because they're alkanes, they're non-polar. And because they're non-polar, they only contain temporary dipoles. Now, the strength of temporary dipoles depends on two things. It depends on the size. Depends on the size of the molecule, specifically the number of electrons, and stackability, like how close the molecules can get to each other. So in this particular case, both propane and nonane are long linear chain molecules, so the stackability doesn't come into play. So it's the electrons here that make the big difference. So nonane has a larger molar mass. It's got a molar mass of 128 compared to 44.1. Therefore, it's got a larger electron cloud. Therefore, it's going to have stronger temporary dipoles. And the trick to these questions is you need to link the strength of the forces to the boiling point. So because it's got stronger temporary dipoles, it's got stronger attraction, more energy is needed to break or overcome the bond, and therefore it has a higher boiling point. Okay, so stronger temporary dipoles, this means the attractions are stronger, so more energy is needed to break, therefore it's got a higher boiling point. Alright, the second one, you're given two funny molecules, butane-1-thiol and butane-1-ol. Again, you've got to recognise what forces are there. So starting off with temp dipoles, both contain temporary dipoles. And the thiol is stronger because it's got a larger molar mass. So in brackets, more electrons. Okay, now thiol has a hydrogen connected to a sulfur, which is going to be a polar bond. Therefore, this is going to have permanent dipoles. Hydrogen is connected to an oxygen, which is a polar bond, so it's going to have permanent dipoles. So both have permanent dipoles. But in this particular case, the butanol, so I'm just going to call it O with shorthand, is stronger, as O is more electronegative. Okay, so because O is more electronegative, that bond is going to be more polar, therefore the permanent dipoles are going to be stronger. The big thing that separates them is because butane-1-ol has a hydrogen bonded to an oxygen, also going to have hydrogen bonding. So the combination of H bonding and stronger permanent dipoles leads to stronger attractions overall. Therefore, more energy is needed to overcome them. Therefore, it's going to have a higher boiling point. And that's reflected in 118 compared to 98.5. Question 3. Write the equation for which the enthalpy change is the enthalpy of formation of ethane. So in Year 13, there's lots of new enthalpies that you have to remember and be able to talk about. So enthalpy of formation is how much energy it takes to form 1 mole of a specific chemical. So in this particular case, we're talking about ethane. So start off by writing your chemical on the product side. You then need to identify what atoms make up that particular compound. So we can see that it contains carbon, and we can see that it contains hydrogen. Your next step is to try and think or work out how those elements exist if they were sitting in front of you. So carbon just exists as carbon atoms, hydrogen exists as H2 molecules. Next up, you have to balance it. We've got 1 carbon on the left, we've got 2 on the right, so we're going to put a 2. We've got 2 hydrogens on the left, we've got 6 on the right, so we're going to put a 3. And the final step, just for completeness, is to put the states. So carbon at room temperature is a solid, hydrogen is a gas, and ethane is a gas, because they told us up there. Alright, number 2, calculate the enthalpy change for the combustion of ethane given the enthalpies of formation below. Now, because all of them are enthalpies of formation, you can use that shortcut. So the enthalpy of combustion is equal to the sum of the enthalpy of formation of the products minus the sum of the enthalpy of formation of the reactants. So products in our case are CO2 and water. We've got 2 lots of carbon dioxide plus 3 lots of water. And reactants, we've got 1 C2H6 and then 3.5 O2s. And from here we just need to plug in the numbers. So carbon dioxide, you're told up here is minus 394. So 2 times minus 394. Water, you're told is minus 286. Ethane, you're told is minus 83.8. And the enthalpy of formation of any element is always 0. So chuck this in your calculator. And you should get this. And when you minus a minus, you plus it. So you get a final answer of 1562 or 1560 to 3 significant figures. Right, if you get a chance, please double check your calculations. It's always painful when marking when you see someone's done everything perfectly. They've written it all down right and then they've put an incorrect number in or misread something and they get the wrong answer. So please double check if you get the chance. Alright, the third question. Calculate the enthalpy change for the reaction below using the data given. So we are trying to work out the enthalpy change for ammonia turning into N2H4 and hydrogen gas. Now we can't use the shortcut in this particular case because we're given enthalpies of reaction rather than enthalpies of formation. So what we need to do is we need to use Hess's law to try and work this out. And what Hess's law involves, or what it states, is it doesn't matter what path you go, it doesn't matter how you go from this to the products, the enthalpy change is going to be the same. So an analogy I use is if you think about the distance between Wellington to Auckland, it doesn't matter whether you drive up the west coast, it doesn't matter whether you drive up the east coast, it doesn't matter whether you wiggle your way up the middle, the distance as a bird flies from Wellington to Auckland does not change. And that's what Hess's law is trying to tell us. So what we're going to do is we're going to try and use these 4 equations to create this top equation. So we have to manipulate these equations to try and recreate the top equation. So what I mean by that is the top equation, it starts off by saying 2NH3. So we need to find ammonia, NH3, in one of these equations. And you'll see pretty quickly that only equation 1 contains ammonia. So equation 1 is what we're going to use. Now, differences between equation 1 and what we want. What we want is on the left-hand side in our target equation. Equation 1, it's on the left-hand side, so that's a good start. Our target equation, there's 2 moles of ammonia. The equation we're given has 4 moles of ammonia. Okay, so we need this to say 2 moles of ammonia. So what we do is we divide equation 1 by 2, and that will give us 2 moles of ammonia. So when we do that, we get 2NH3 plus 3 over 2 oxygen goes to N2 plus 3 waters. And when you half an equation, you half the enthalpy, so that goes to minus 765.5. Okay, so ammonia is done. I'm going to do hydrogen next. We need 1 mole of hydrogen on the right hand side. Looking at our equations, only the third equation here has hydrogen, so we're going to use equation number 3. And looking at the differences, we want 1 mole of hydrogen, 1 mole of hydrogen. We want it on the right hand side. Hydrogen at the moment is on the left hand side. So what we need to do is reverse equation 3. And when you reverse it, the hydrogen will become on the product side. So water will become hydrogen plus half O2. And when you reverse an equation, you change the sign of the enthalpy. So this becomes positive 242. Alright, so we've done hydrogen. The last thing we want is N2H4 gas. Okay, so looking down, the only equation that contains N2H4 gas is this last one here. 2 doesn't count because that's a liquid. We can only use this one. So we're going to take number 4. We want 1 mole. We've got 1 mole. We want on the right hand side. It's on the right hand side. So we can just write that equation as it is. Plus 10. Okay, so with Hess's law, what you do is you manipulate your equations like we have here, and then basically you add them all together and simplify it and cancel terms out, And when you do that, you should be left with your target equation. And if you're left with it, you know you've done it right. Now, hopefully you can see pretty quickly that this equation we've just used has N2H4 as a liquid, and when we look at our target equation, there's no N2H4 as a liquid. So we need to get rid of this somehow. We can't just delete it, it has to be cancelled out somehow. So if you look at the equations we're given, only another one contains N2H4 liquid, which is number 2. So we're going to use number 2, and if we look at what we have, we've got 1 mole of liquid here, we've got 1 mole of liquid here, that's good. This is on the left-hand side, this is on the left-hand side. So if we want them to cancel out, we actually need them to be on opposite sides. So what we're going to do is we're going to reverse equation number 2 to put that on the right-hand side. So when you reverse it, you get this, and of course when we reverse it, we change the sign. Alright, so theoretically, if we add everything together and simplify and cancel it out, we should get that target equation. 2 ways you can do it. You can basically write everything that's on the left-hand side down here and everything that's on the right-hand side down here and just add it together. Or you can go through and just simplify things as you see it. So if we take, I'm just going to do it a simple way, on the left-hand side we have an N2H4 liquid, on the right-hand side we have an N2H4 liquid, so they can cancel out. On the left-hand side we have 1, 2, 3 waters, on the right-hand side we have 3 waters, they can cancel out. On the left-hand side we have 1 nitrogen, on the right-hand side we have 1 nitrogen, they can cancel out. So, what have we got left? We have 2 NH3s, oh, I forgot something. On the left-hand side, we have 1.5 O2s. On the right-hand side, we have half an O2, 1 O2, 1.5 is, or 1 plus a half is 1.5. So they can all cancel. Now what we're left with is, on the left-hand side, we've got 2 ammonias. On the right-hand side, we've got an H2 plus an N2H4 gas. And you can see this is exactly the same as what our target equation is. So what we do now is we just add together all of the enthalpies. And if you do that, the enthalpy change is 108.5 or 109 kilojoules per mole minus 1. Right, next up is a calorimeter question. So we're dissolving a solid into a liquid. It's got a temperature rise and we're trying to work out the enthalpy of reaction. So this is a kind of 2-step process. Number 1, we have to work out how much energy is involved. And to do that, we need this formula here, Q equals mCT. So M stands for the mass of the solutions or whatever you're dealing with. C is the specific heat capacity. So how much energy it takes to heat up 1 mol of a solution by 1 degree. And T is the temperature change. So in this particular case, we've got 7.15 grams of barium hydroxide is added to 100 grams of water. So when you add the 2 things together, that gives you a total mass of 107.15. Specific heat capacity, they'll always give you, in this case it's 4.18. And the temperature change, they tell you, is the temperature falls by 2.9 degrees. And because the temperature's gone down, it's a minus. So chuck that in your calculator, you get minus 1298.8 blah 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 joules. So that's your first kind of tripping point. Q is always calculated in joules. And we can convert that to kilojoules by dividing by 1,000. So 1.298 kilojoules. Now apologies for the screen flashing all the time. I thought it might just be me as I'm going along, but it looks like it's coming on the video as well. Hopefully it doesn't cause any issues. So the first step is to work out how much energy is involved. The second step is to work out the enthalpy change. So we use this formula, minus Q over N. Now you're only given one of these formulas. I can't remember which one, but you're only given one of them. You have to remember what the other one is. So Q minus Q, we worked out what Q was up the top. So minus 1.298 divided by N. So N is the number of moles. We need to work out the number of moles of chemical. So we are adding together barium hydroxide to ammonium thiosulfate. So we need to work out the number of moles of chemical, and it's either the number of moles of barium hydroxide or the number of moles of ammonium thiosulfate. thiocyanate, sorry. And if the two values are different, you always use the smallest number because that's the limiting factor. In this particular question it says, there was sufficient ammonium thiocyanate for all barium hydroxide to react. So what that tells us is that we have lots and lots of this ammonium thiosulfate and that the barium hydroxide is the limiting reagent. So we're going to work out the number of moles of barium hydroxide. So to work out the number of moles of barium hydroxide is equal to mass over molar mass. You're told the mass was 7.15. You're told the mass was 7.15. You're told the molar mass is 316. Chuck that in your calculator and you get 0.0226 moles. So we can then chuck that number in up here, 0.0226, and when you do that you get a final answer of 57.2, and the unit for enthalpy of reaction is kilojoules per mole minus 1. Lucky last. We've got an entropy question. So nitrogen triiodide or touch powder is a solid that explodes on contact, producing a loud bang in a cloud of iodine gas. So some of you may have seen this demoed earlier this year. Explain the entropy changes associated with this reaction and hence why it is spontaneous. So entropy, what it is, it's a measure of disorder. And when you're talking about entropy, you have to talk about the entropy of two things. You've got the system and the surroundings. So if you have a reaction taking place in a beaker, this is what you call the system. And the surroundings are the things outside the beaker, like the air around the beaker. So you have to talk about the entropy change for both of those things. So in terms of the system, there's a couple of different ways that entropy can change. Number one, if there's a temperature change. So if something heats up, particles move faster, therefore because they're moving faster, there's more disorder, so that's an increase in entropy. Second thing that can happen is if you change the number of moles. So in this particular case, we've got 2 moles on the left, on the right hand side we've got 5 moles. So when you go from 2 moles to 5 moles, you increase the disorder. The total number of arrangements for 2 things is a lot simpler than the different arrangements that you can get for 5 things. Okay, so because we've gone from 2 moles to 5 moles, and because we've gone from a solid to a gas, both of those things increase the disorder. And when disorder increases, you get an increase in entropy. Okay, in terms of the surroundings, that flashing is really annoying. Surroundings, this reaction is exothermic because we're told up here it's a negative enthalpy of reaction. What that means is energy is given off. In this case, it's heat. So because it's exothermic, the surroundings are going to heat up. And when surroundings heat up, they move faster. When things move faster, there's more disorder. And when there's more disorder, you get an increase of entropy. Right, the final catch of the question, it says, explain the entropy changes associated and hence why it is spontaneous. So we need to link our two ideas to spontaneity. So because entropy has increased for both, so positive entropy is increased for both, and on a side note, because it's exothermic, this makes the reaction spontaneous. And exothermic, so because of these two things, reaction is spontaneous. Right, so hopefully that clears up all the questions in this particular paper. Again, sorry for the flashes, hopefully it hasn't caused you to have any issues. If you have any further questions, please go ask your teacher or flick me an email. Cheers.